Alright, so let's go ahead and continue talking about the same example that we had before. We left off and I mentioned that it's possible for a system to sort of level out and maintain a constant state after a certain amount of time. And if that happens, then we have what's called a steady state. And so it's possible to find that state matrix where the system is going to level out to, given the transition matrix. So we're going to say that a state matrix X is a steady state matrix. So the term we're defining here, the steady state matrix, if and only if the state matrix times the transition matrix gives us back the state matrix. So the reason it's called a steady state is because the state matrix will remain unchanged even if you go through the transition matrix. So in order for us to find a steady state matrix, we're going to have to solve for that matrix X. So we've been given the transition matrix and we want to find the state matrix. So we'll use our previous example. Remember the transition matrix from the previous example was 0.2, 0.08, 0.8, and 0.92 from the previous example with people getting in accidents. So if we're going to determine the steady state matrix, our matrix X is going to have two entries. And that's because our transition matrix is a 2 by 2 matrix. So that tells us that we have two different states, and so the state matrix must have two entries. Now we don't know what those entries are, so we're going to call them X and Y. So we know, here's our state matrix. We have no idea what it is, but it has to have two entries and they're both unknown. So if we take X times XY, the matrix that we are calling X, right, our state matrix, and we multiply it by the transition matrix, 0.2, 0.8, 0.08, and 0.92. So if we multiply it by the transition matrix, then we should get back the matrix X that we started with. So we should get back our unknown matrix X times Y. Okay? So we're using our definition in order to set up this equation. So now let's go ahead and solve this. I'm going to get rid of this line so we have enough room here. So let's see, if we multiplied this matrix out, so if we do the matrix multiplication on the left, we would get 0.2x plus 0.08y. And for the second column, we would get 0.8x plus 0.92y. That would be our multiplication for the left-hand side. Now this 1 by 2 matrix has to equal x, y, the matrix x, y. So now we have two equations that have emerged from here. The first entry on the left-hand matrix must equal the first entry from the right-hand matrix. These must be the same, because two matrices are equal if and only if their entries are equal. Similarly, the second entry for both matrices must be equal. And so now we have two equations. And it turns out that we only need to solve one of them. So you can choose one or the other to solve, but it doesn't matter, but you're only going to need one of them. So I'm just going to take the first one here. So we have the 0.2x plus 0.08y has to equal x. Now we also have another fact, and this is important to recognize. The original matrix XY is a state matrix, and so that tells us then that if we add up the row x plus y, we should get 1, because x and y are probabilities, not just random numbers. So now we have a system of two different equations, and we can go ahead and solve for x and solve for y. So let's see, if I start with the second equation, I'm going to rewrite y as 1 minus x. And so then the first equation, we get 0.2x plus 0.08 times 1 minus x equals x. And then I'll let you finish it from here, but we should end up with, so there's a couple steps in between. X is equal to 0.090909. And this is an approximation, so about 0.090909. Now if x is approximately 0.090909, then we get that y is approximately 1 minus 0.090909. And so we have that y is approximately 0.909091. Okay. And so we can say then that our steady state matrix, so x equal to the steady state matrix, first entry is 0.090909. I'm going to run out of room, so let's rewrite this. So x equal to 0.090909, and then the second entry, 0.909091, is the steady state matrix. So this is the steady state matrix for this system. What that means is that in the long run, so if the system remains unchanged and kept going forever, we should expect that every year we should have about 9.09% of drivers in a car accident, and about 90.9% of people not in a car accident. And if you look back at the previous example, we started to see this at about 5 years. At the 5-year mark, we ended up with the percentage of people in an accident at about 9.09%. And that's what the steady state matrix says as well. So this is describing the long-term behavior of the system. So if the system kept going, we should expect it to sort of level out at 9.09% of drivers in a car accident and 90.91% of drivers not in a car accident in the long run. Okay. Anytime you're trying to solve for a steady state matrix, you must use the fact that x plus y is 1, and you only want to use one of the two equations that you get from the multiplication. If you don't use the x plus y equals 1 fact, then you sort of end up in a circular pattern. So you'll never be able to solve for just x or just y. You'll keep going back and forth in between them. So you want to choose just one of the equations from the multiplication, and then also use the fact that x plus y must equal 1. Alright, that's all for now.